It's a this one. Let's try. Okay. So.
Hi, everyone. So our next speaker is Florian Deuber. He's a master's student on the Electrical Engineering and Information Technology Masters at ETH Zurich, with a focus on computers and networks and electronics and photonics. And his research interests lie in hardware-software interfaces, co-design, memory, accelerators, and he's interested in pursuing a PhD or going forward with a career in embedded systems. The stage is yours, Laurie.
Thank you for the introduction, Konstantinos. And welcome to all of you to my seminar about the paper I have the honor to present called Virtuoso, enabling fast and accurate virtual memory research via an imitation-based operating system simulation methodology. Before we dive into Virtuoso, let's quickly recap virtual memory. Virtual memory is a cornerstone of modern computing systems. And to give you a high-level overview, it is a hardware operating system mechanism that gives each process the illusion of having its own large private contiguous address space. The CPU's MMU, memory unit, translates virtual addresses to physical addresses using operating system managed page tables. This process is called paging, and only some pages are kept in RAM at a time. Others may be stored on disk and brought into the RAM on demand, with pages being evicted when space is needed. Now the question is, so why do we actually need virtual memory? So first off, when you write your program, you don't have to take into account the physical memory that lives inside the system. So you can basically ignore how physical memory is organized. Secondly, we can isolate programs. Each program runs its own protected address space, so bugs or malicious code can't easily corrupt others. So, and lastly, we can share data between processes. The operating system can map the same physical pages into multiple processes, so they can efficiently share code or data. All right. To go a little more in depth how virtual memory actually works, as I've already hinted at, programs have a virtual address space, while the physical memory has a separate address space altogether. There we split both the virtual and physical address space into chunks, which we call pages, and these pages are in most systems 4 kilobytes. How do we make virtual addresses point to the physical addresses, you might ask? So when you touch your data, you need somehow install it from the virtual address space and make it point somewhere in their location in the physical address space. This happens via the virtual to physical address mapping. So you can think of it as a directory where we essentially store information about where this virtual address is stored inside the physical address space. And this can map to anywhere in the physical system or space. So now the question is, who creates the address mapping between the virtual and physical addresses? So again, you have an application here, and it has its own virtual address space, right? And you can see this page on the left, and you can see the physical memory. And at some point in time, the virtual addresses on the top that is chunked, we need to map it somehow to the physical memory. But the question is, who does that? We get the fault because the mapping is not established yet. and no one has established it till now. So yeah, so someone needs to map this virtual address to the physical memory. And there is where the operating comes in. It takes over in modern systems. So the operating system handles the memory allocation and establishes the mappings for us. We stop the application basically because the mapping is not established yet. And then the operating system, the first thing it tries to do is find free space in the physical memory to place our data, our virtual page. This is called a minor fault. If though the data needs to be fed from disk, for example, you want to read the file using your program. This is a file back data and it's not already stored in memory. So it's somewhere in the disk, then you first need to fetch it from the disk and find free physical space in the physical memory. And that's what we call the major page fault. It's a lot more expensive to have a major page fault compared to a minor page fault. Once the operating system does this, then it somehow needs to store or update the virtual to physical address mapping, and this is done through the page table. So when the operating system is done with allocating memory, it goes and updates the page table, which also lives inside the memory. The question is, okay, we have a page table now, right? The operating system did its job by updating, inserting the mapping. The question is, how does the hardware figure out when it wants to load the virtual address? What is the actual physical address that is stored inside the physical memory? Through the process of address translation, we ask ourselves, what does this process look like? The core, when it needs to access a specific virtual address, it ships a packet to the memory management unit. The memory management unit is a hardware component which is responsible for one thing, creating a virtual address, giving back the physical address while the program is running. How does it do that? It needs to somehow load the data from the memory hierarchy, do some magic, as I will show later, and do this very fast. This happens for every virtual address. Every virtual address needs to be translated to a physical one in basically all modern systems. How does the memory management unit look like? There is a component first, a bunch of components, which we call the TLBs. These are the translation look-aside buffers. So the translation look-aside buffers store virtual to physical mappings directly. So using the virtual address, we can derive the physical address, and these are classes that are store these sort of mappings. When we miss in the TLB hierarchy, then we need to find the virtual to physical mapping via accesses to the page table. And to load the page table, we need to go to the memory hierarchy. We could also look at this in more depth, but I already have lots to talk about. So if you want to know more about this, you can look at lecture 4 of the seminar, where Konstantinos will went into more detail of this. So the problem now is it doesn't come for free, right? It causes high performance overheads because of two things I just discussed. The first one is memory allocation. So first, when we want to install our data and establish the virtual to physical data mapping, we need to pay a high price to achieve that. And secondly, the address translation also. When we want to translate virtual addresses to physical addresses, again, we need to perform high price in terms of per access the page table a lot. All right. To rephrase it a bit, the challenge in modern workloads is that it spends a large fraction of time in virtual memory operations, but existing simulators are either fast and VM inaccurate or accurate and too slow. So this paper proposes an approach called Virtuoso, which co-simulates hardware with a structure called Mimic OS, which is a lightweight user space kernel that imitates Linux's memory management. The key idea here is to run only VM-related operating system code and feed its real instruction stream into existing simulators. And this results into much more realistic VM behavior and IPC estimates with modest overhead without the complexity of a full system simulation. And the impact of the paper is basically that it provides a practical, extensible platform for hardware operating system co-design in virtual memory research. So this is the outline we're going to look at today in terms of the paper. First, we'll start with a problem and motivation. Then we have a look at the high-level Virtuoso, then look at its architecture and workflow. Afterwards, we're going to also talk about the aforementioned Mimic OS and also about WordTool, which is basically a tool set for this whole structure. And after that, looking at the evaluation and some use cases. So let's first start with problem and motivation. So virtual memory is now a major performance bottleneck, especially for short and long-running workloads. We come back to this. This is an example of a short-running workload, a single inference request to a large language model. It's not a long HPC job, a few seconds at most. However, the model still uses many gigabytes of memory. And to serve just one request, the system may have to allocate pages, handle page defaults to bring model weights into memory, or warm up TLBs and caches and so on. So yeah, short-running workloads, their short runtime is too short to amortize operating system overheads like page allocations, which can take up to 95% of execution time. The paper shows that memory allocation overhead is around 32% on average, while the overheads of address translations are only less than 1% on average of total execution time. And yeah, this is an example of a long-running workload, a large-scale graph analytics on a huge graph with millions of nodes and edges. Algorithms repeatedly traverse the whole graph with very irregular memory accesses that cause many TLB misses, page walks, and page faults over the long execution time. Due to this, virtual memory behavior can dominate the total runtime, and workloads like this appear in social network analysis, bioinformatics, cybersecurity, or also in transportation. For example, the classic, you either love it or hate it, the traveling salesman problem. Given many cities, we search for the shortest possible tour, and the number of possible routes grows explosively. So real solvers run a long time and touch a huge amount of memory. And under the hood, this is again a graph of optimization workload with irregular memory accesses. So VM behavior and TLB page table performance really matter. And yeah, long-running memory intensive workloads, they can consume up to 40% of execution times in terms of address translation. And the papers, according to the paper, on average 25% in address translation and 5% for memory allocation. So yeah, VM overheads are also getting worse with ever larger memories and more complex systems. These are some examples. Again, if you want to know more about them, you can look at lecture 4. But I just wanted to bring an example, memory disaggregation. Think of a server in a data center that has some local DRAM next to the CPU, but it can also rent extra memory from several remote memory boxes over a fast interconnect like CXL. To the application, this looks like one big memory, but physically it's one local memory and multiple remote memory nodes spread across the rack. Virtual memory now has to manage a much larger distributed memory space or address space and decides where each page lives. So VM overheads and address translation complexity increases compared to a single local memory system. But worry not, researchers are here to save the day. To improve virtual memory, many recent works co-design hardware on operating systems, from software-managed TLB subsystems over leveraging VA to PA contiguity, to accelerating memory allocation, alternative address mappings, rethinking the page table design, also employing multiple page sizes, and many more. Now that we have such a wide range of hardware operating system co-design techniques, you would think we're set, right? You would be right, except for one problem. Evaluating these designs is hard. The two main classes of simulators to evaluate these designs are firstly the emulation-based simulators. These are fast, but usually model OS VM using crude first-order approximations by analytically estimating VM overheads. What do I mean by that? Typically, they count things like TLB misses and page faults, and then multiply by a fixed cost per event. The problem is that these latencies are not fixed in real systems. They depend on cache hits, DRAM contentions, huge pages, swap, and so on. These miss the large variability of VM behavior across workloads and system states. In contrast, the full system simulators simulate a real operating system in all its aspects, but are quite slow and very memory hungry and hard to extend, because you have to do kernel hacking or simulator hacking, which is again overhead in work time. You have to take into account. So today you choose between fast but inaccurate, or accurate but painfully slow and complex, which is particularly bad for VM research that spans both hardware and operating system. Yeah, now let's take a look at the high level of Virtuoso. Virtuoso is a new simulation framework that aims to bridge the gap between emulation-based and full system simulators. It uses a lightweight user space kernel called Mimic-OS, written in a high-level language, here C++, which imitates only the VM-related parts of an operating system, roughly Linux's memory management subsystem, instead of the whole system, the whole kernel, full-blown kernel, right? To give you an intuition, Mimic-OS runs a separate user space process alongside the architectural simulator and communicates with it via, firstly, a functional channel to exchange events and their results, and also an instruction stream channel to feed the instrumented Mimic-OS instruction streams into the simulator's core model, so that OS routines incur realistic timing and microarchitectural effects. For example, cache pollutions, DRAM contention, etc. So yeah, the key goals here are basically a speed close to the emulation-based simulators, accuracy closer to filled system simulations for VM behavior, and also a lower developer effort. So we have to do no kernel hacking, basically, and so we can write the OS logic in C++ or Python, and also make use of high-level libraries. This paper calls this an imitation-based operating system simulation methodology and positions it as a third point between emulation and full system. All right, now taking a look at the architecture and workflow. Conceptually, we first have the architectural simulator, which executes a workload. Then when a memory access occurs, a TLB miss and page table walk that fails, the MMU model triggers a page fault event. Via the functional channel, the simulator sends this event to the Mimic-OS. The Mimic-OS runs its page fault handler and other operating system code. During this, a binary instrumentation tool records the dynamic instruction stream of Mimic-OS's code. That instruction stream is sent via the instruction stream channel to the simulator's core model. And then the core model executes these micro operating system instructions, so the latency and micro-architectural effects are modeled. Once Mimic-OS finishes, it writes back the result via the shared memory and signals the simulator. And lastly, the simulator resumes the application, rewalks the page table, and continues. The same pattern applies to other VM-related operations, for example, allocations, swapping, huge page policies, and so on. And Mimic-OS also supports multi-threading. enabling it to handle concurrent requests like page faults from different cores, and model contention on operating system data structures via synchronization primitives. So yeah, now that we've taken a closer look at Virtuoso as a whole, let's turn our attention to the already mentioned Mimic OS and get a high-level overview of it, shall we? All right, what is Mimic OS, you might ask? It's a small user space kernel that imitates Linux's memory management, as I already mentioned, and it handles the page faults, page tables, huge pages, swapping, and the page cache. Looking at it at a high-level behavior standpoint, it firstly figures out which virtual region the faulting address belongs to. It decides how to map it, and then walks a Linux-like multi-level page table and allocates any missing metadata. After looking at the page size decisions real quick and very roughly, it tries to use large pages first and foremost, either 1 GB or 2 MB, depending when the layout and policy allow it. Else it falls back to 4 KB pages when these large pages are impossible. And it can also promote groups of small pages into larger ones in the background. Looking at the backing storage behavior, for anonymous memory, it may need to pull pages back in from swap. And for file-backed memory, it controls the page cache and may simulate disk I/O on a miss. So why this matters for the simulator, you might ask? Well, different faults cost very different amounts of time, cheap versus expensive faults in this regard, right? Mimic OS reproduces that realistic variability of page fault latency instead of using one fixed cost. This is achieved through the interplay of different modules. And lastly, this makes VM behavior in the simulator much closer to a real Linux system. All right, so far we've talked about Mimic OS. Let's accurately model Linux-style virtual memory behavior that lets us do that. And next I want to show how we turn that into a toolbox for VM research they call Virtool. So this table compares different simulation platforms in terms of which virtual memory mechanisms they can actually model. The rows are simulators, classic emulation-based ones at the top, full system simulators in the middle, and the Virtuoso at this work basically at the bottom. And the columns are the key VM features researchers care about. And most existing emulation-based simulators only give a fairly generic choke components. You can't easily explore newer ideas like range translation or hash-based page tables. So yes, and full system simulators support a bit more, but here's the problem. Every study tends to build its own one-off infrastructure, and you still can't get all these mechanisms in one place. This is where Virtool comes in. We intentionally implement many of these VM schemes in a single framework. The idea is that instead of building a new simulator for every VM paper, you can prototype and compare all these techniques with one consistent Mimic operating system-based environment. So yeah, using Mimic OS as the operating system side, the offers integrate Virtuoso with 5 simulation platforms. First, we have Gem5 SE, the little brother of Gem5 full system. It's basically run in syscall emulation mode. Then we have Remulator 2, a detailed main memory simulator. Also the main platform in the paper, the Sniper, which is an interval-based micro-architectural CPU simulator. GemSim, a trace-based cache TLB simulator. And lastly, MQSim, which is an SSD simulator for modeling page caches or swap disk latency. And yes, the integration effort is quite modest, tends to a couple hundred of lines of code per simulator, which makes it very feasible to implement in a short amount of time. And which also works with trace-based simulators by streaming MimicOS's instructions as an additional trace. GemSim is a classic trace-based simulator. It normally just replays an application trace and has no real operating system running in the loop. With Virtuoso, whenever GemSim's MMU model hits a page fault, it sends that event over to the MimicOS on the left. MimicOS actually runs the page fault handler, and they used an Intel pin tool to record the exact instructions that this handler executes. And those MimicOS instructions are then streamed back to the GemSim as a second trace. The core model simply injects them between application instructions as if the OS code has been part of the original trace. And so GemSim can now see cache misses, the TLB activity and stalls caused by the operating system code, even though it's still just a trace-driven simulator, right? But which also can also do that for execution-driven simulators by dynamically switching between application and MimicOS instruction streams, and also in emulation-based simulators like Gem5 by reusing existing emulation infrastructure to feed MimicOS's instructions. All right, now having a closer look at the evaluation, the setup was they mainly used Virtuoso plus Sniper as the testbed, and they compare against the real server, the Intel Xeon Gold, and they mainly looked at two kind of workloads. On one hand, long-running Ref and HPC apps with heavy address translation pressure, and on the other hand, short-running apps, fast-like functions, LLM interference, image processing kernels, and so on. Now, looking at the accuracy versus the real hardware, the key findings here are that in MMU behavior, the L2 TLB MPKI and page table walk latency are modeled with 82% and 85% accuracy, respectively, versus the real machine. Looking at the page fault latency, the per fault latency distributions have a cosine similarity of around 60% on average, up to 79 for some workloads. Then looking at the IPC estimation, the baseline Sniper with fixed page table walk latency achieves around 66% accuracy, while Virtuoso plus Sniper, so with the MimicOS installed, achieves around the 80% accuracy. That's about a 20% relative improvement. And looking at the simulation overheads, using the worst case, a micro benchmark with many page faults, adding MimicOS causes around 20% average slowdown across 4 simulators. For Gem5 full system, the Gem5 full system is 70% slower than the Gem5 SE, while MimicOS offers similar VM accuracy with much lower overhead. And looking at the memory usage, the MimicOS adds 1.45 times average memory consumption across simulators, while the Gem5 full system uses around 2 times memory compared to Sniper plus MimicOS. And yeah, they show a strong linear relationship between the fraction of instruction executed in MimicOS and a simulation slowdown, which is intuitive, right? So more operating system work leads to more simulated instructions. All right, now let's look at some use cases. In the paper, they talked about 5 different use cases. In lecture 4, you will already find the physical memory allocation for LLM inference use case discussed more accurately or in detail. And I want to focus on these 2, page table designs and intermediate address space. and basically go into more detail in the page table designs and only touch upon the intermediate address space for you to get an idea what it's about. So looking at the page table designs, we all know the radix trees, and they are today's default page tables. These are where you traverse the page table step by step to obtain the physical frame numbers, then combine it with the page offset to form the final physical address, right? But many papers propose hash-based page tables. With Virtuoso, we can ask, if I only change the page table structure, what really happens to translation, latency, and DRAM behavior? So treat these as three flavors of hash-based page tables, all aim to reduce the number of memory accesses per walk, but they differ in where those accesses land in DRAM. And all three hash-based designs reduce page table walk latency compared to radix. Benefits are largest when memory isn't badly fragmented, so we get more large pages and fewer levels to traverse. If you only looked at this metric, you'd say hash-based page tables win, done, right? But it's not that easy. Radix tends to touch page table entries in a relatively structured way compared to, for example, the ECH, which spreads entries out more aggressively. That reduces latency per walk, but scatters accesses across DRAM rows. And this results in the ECH increasing row buffer conflicts, while HTC and HT slightly reduce them versus the radix. And yeah, what you have to get from that, basically, this use case shows Virtuoso isn't just giving us more numbers. It lets us discover that faster page walks can secretly mean worse DRAM behavior, depending on the design. And yeah, page tables designs must be evaluated end-to-end, latency and memory system effects, and Virtuoso lets us do that without changing anything except the page table. All right, now looking at the intermediate address space as a use case, the page tables are tightly tied to the physical layout. Anytime we move data around, we pay to touch a lot of per process metadata. And think of IA as a handle. Think of IA as a handle. The program's virtual addresses keep pointing to the same handles. The operating system can change where those handles point in physical memory without rewriting every virtual address entry. All right. The problem here is IaaS is not free. We're buying layout flexibility and smaller metadata by adding another lookup. So the real question is, when does that trade-off pay off? And because Virtuoso models both the hardware lookup and operating system policies, it can tell us for which workloads the extra level is worth it, instead of assuming the intermediate address space is always good or always bad. So intermediate address space inserts a VA, IA, PA indirection. It doesn't change what the program sees, but it changes how flexible the operating system is in laying out memory. So, which also lets us, again, test that trade-off end-to-end, hardware and operating system, so we can see when IaaS is a win and when it's just extra overhead. All right, now let's turn our attention to some strengths of the paper or the whole project as a whole. So first, it is the first simulator to bridge an emulation-based and full system with VM simulation in terms of speed and accuracy. So far I know of. And it has a realistic VM behavior with modest cost. It models page faults, THP, page cache, and swap in detail while adding only around 20 to 30% simulation overhead. It has a general reusable infrastructure. It integrates with multiple simulators and ships Virtool, a rich toolkit of VM mechanisms. It's also thoroughly validated. It matches real hardware across TLB, MPKI, page table walk latency, page fault latency, distributions, and IPC, far beyond simple runtime matching And lastly, it's open source and ready for adoption. So if you want to use it, you can. Lowering the barrier for future hardware operating system co-design work on virtual memory. So yes, now turning attention to some weaknesses. You have to keep in mind, it is not a full system replacement. It cannot model non-virtual memory operating system behavior the way Gem5 full system or real kernels can. Its coverage is tied to the Mimic OS, so fidelity depends on how closely Mimic OS tracks Linux's VM paths. The kernel changes or obscure corner cases may not be reflected. The manual extension effort is also a point. Adding new subsystems requires non-trivial Mimic OS engineering. And the extra overhead versus pure emulation is also a point. The last point I'm going to mention here, which shows that more realistic VM behavior comes with added simulation time and memory use compared to simple fixed latency virtual memory models. All right, now we've reached the discussion point. So first, do you have some questions? All right, let's go. So first, for your own virtual memory management unit projects, would Virtuoso be good enough compared to full system simulation? Or would you still insist on running a real operating system? So my take would be, for virtual memory-centric work, I would consider Virtuoso good enough in most cases. It gives me realistic page fault paths, THP behavior, page cache, and swap. It's much better MMU and IPC accuracy than than a fixed latency virtual memory model. And it gives a big reduction in engineering effort compared to hacking a real kernel or Gem5 full system, right? But I'd still fall back to a full system setup if my project depended heavily on non-virtual memory subsystems. For example, complex interrupt behaviors, scheduling decisions, or intricate input-output stacks. But for page tables, TLBs, allocation policies, and intermediate address spaces, which also hits a good speed accuracy sweet spot. So the second question is, do you trust the user space imitation of Linux's VM paths for accuracy, or are there specific corner cases where you would expect it to break down? I would trust it for the common performance critical virtual memory paths because these are implemented explicitly in Mimic OS. The paper validates them against hardware across TLB events, page table walk latencies, and page fault latency distributions. But where I'd be more cautious with is with raw kernel features and also with kernel versions that diverge significantly from the Linux baseline Mimic OS models, and also interactions with subsystems, which also doesn't model yet. So we can say it's accurate for the hot path, in quotation marks, right, of virtual memory behavior, but I wouldn't use it to reason about every obscure kernel corner case. Next question. What does this imitation-based operating system approach imply beyond virtual memory? So could we build similar lightweight Mimic OS-like kernels for other domains? Yes, that's one of the most exciting implications. The main idea is to pull just the relevant operating system subsystems into a user space mini kernel and co-simulate it with hardware. For storage, you could imagine a Mimic OS style stack that imitates the page cache, block layer, and an NVMe driver to study controller and queue designs. For networking, a lightweight kernel could let you explore offload engines or smart NICs without full network stack, Or for accelerators, you could model input-output MMUs or unified virtual memory behavior with a small device operating system that runs only the memory management and runtime code paths. Which also shows that this pattern is practical for VM. The broader implication is that we can build domain-specific, high-fidelity mini-kernels that give us much of the realism of a full system, operating system, but at a fraction of the complexity and simulation cost. What would it take to push Mimic OS even closer to Linux, but keep the overhead low? So I would profile first, then imitate. Basically measure where the real Linux kernel spends time in the VM paths, and extend Mimic OS only along those hot paths so that it spends a similar amount of time on the same operations. And also selective fidelity, not just full fidelity, meaning adding detail only for code that is frequently executed or performance critical. So keep rarely used features as simpler models or fall back to fixed latencies. And also the point corner cases versus cost, right? Decide which corner cases are worth modeling and provide hooks so that uncommon behaviors can be plugged in without turning Mimic OS into a full Linux clone. So the last question, can we automate building and calibrating Mimic OS from Linux, and where could LLMs help? From Linux to Mimic OS via profiling. Basically capturing execution traces of Linux's VM paths and use them to derive typical control flow and timing. So how to put it? So to use differential testing, run the same workload on Linux and Mimic OS and compare events and latencies and auto-flag mismatches, basically. And also, always use LLMs responsible, right? Not as the ground truth and only as assistants. Use LLMs to summarize complex kernel code paths and suggest equivalent high-level C++ logic, basically. Have LLMs generate test cases and corner scenarios that Mimic OS should handle. And lastly, let LLMs help maintain documentation and invariants for the Mimic OS codebase as it grows. So last summer, I had the pleasure to have a lab in Fundamentals of Computer Architecture about this Virtuoso. And there I learned some things. What I did was use Virtuoso plus Sniper to explore advanced VM features from the lab, like page sizes, also using hardware page size predictor and THP promotion thresholds. And what I got, the key results from my lab were that huge pages really help, switching from 4 kilobytes only to a mixed 4 kilobytes plus 2 megabytes gave about a 1.75 times speed up, while the L2 TLB MPKI dropped from 70 to 59, and total page table walk time shrank by 93%. Also, the page size predictor had a tiny but positive impact. the predictor unchanged L2 hit MPKI almost not at all, but still reduced total translation latency by around 6.6% with only 0.3% IPC gain. And lastly, the THP promotion threshold is very sensitive, as I learned. Raising the threshold from 0 to 25 to 50% increased total cycles by around 45 and 78% in my case, and made page table walks around 7.9 and 15 times respectively slower. And yeah, my takeaways here is that OS policies and hardware interact strongly. So small configuration changes can move performance by tens of %. And yeah, which also made it practical to run many what ifs and see detailed MMU stats with which matches the paper's goal of fast VM accurate research infrastructure. So yeah, to conclude this seminar, also this presentation, which also central contribution is a practical middle ground. You get substantially better VM accuracy than conventional emulation-based simulators, while you only pay a 20 to 35% simulation time overhead versus the much higher cost of a full system simulation. And you can prototype operating system level VM schemes in C++ or other high-level languages and integrate them into multiple simulators without deep kernel hacking. And yeah, if you're doing virtual memory research, which also gives you a reusable, reasonably accurate, and fairly fast playground to develop and compare designs. That was it from me. Thank you for listening. Any questions?
Yeah, I guess this project, we have been working on it for more than 3 years, I guess, and still working on it. And it got like spawned because, as Florian said, existing simulators had several very, let's say, intense trade-offs. Either you would go with something very simplistic or you would go with something very aggressive and very slow. Yeah, and our vision would be that people implement new schemes on top of this simulator. We are able to basically create a ground for research which is common, so that we don't need to hop between different simulators and make the life of researchers, students much easier, basically reduce the cost of entry into this type of research. Yes.
Thank you. Sorry?
What kind of workloads were those that you reported results for?
Traces they gave us, I don't quite remember.
I gave a trace which is very demanding, basically. It's a 10 gigabyte trace that performs irregular memory accesses. So that no, it's from HPCC, from the workload suite. Yeah, but like with this specific lab, we wanted to see the effect of large pages and page size prediction. So we chose some trace which basically can give you benefits from large pages. In the next one, things change a bit, and we don't focus on page size prediction, different page sizes.
Another presentation. We don't have another presentation for today. So I think we can conclude today's lecture basically, and we'll see you next week. Thank you.